In this video, we're going to take a look at the Wittig reaction, which is a really important reaction in synthetic organic chemistry. It allows you to make alkenes in a very selective manner. So what is the Wittig reaction? Well, it involves a phosphorus ylide. We already talked about sulfur ylides. This is a phosphorus ylide. And a phosphorus ylide will react with a carbonyl, an aldehyde, or a ketone, and it'll make a double bond. And so the phosphorus ylide it can be written two ways. It can be written with a phosphorus carbon double bond or as a Zwitterion, depending on whether you want to violate the octet on the phosphorus. And it reacts with any aldehyde or ketone. And essentially, it's a bit like olefin metathesis in organometallic chemistry. One half of the double bond comes from the aldehyde. The other half of the double bond comes from the phosphorus ylide. And you make the other product, of course, is phosphine oxide. So how do you do this? Well, the making the phosphorus ylides is pretty simple. You take a phosphine, triphenylphosphine most commonly. You alkylate it, just essentially an SN2 reaction. Then you use a really strong base, and we're going to use butylithium, and you deprotonate the carbon attached to the phosphorus, and you make your ylide. And this ylide then will react with your aldehyde or your ketone. So this is triphenylphosphine. It's very sterically hindered. When the steric hindrance is an important part of this. The ylide, here we have one here pictured here, and this of course would be the double bond right here along that direction. And the key thing is the steric hindrance is going to be an important part of our story. And so the aldehyde comes up, and you end up with triphenylphosphine oxide and your resulting alkene. The interesting thing is that the standard Wittig reaction that we're shown here gives you a cis alkene, which is kind of interesting because thermodynamically that is not the most stable. So more properly, of course, Z stereochemistry, but you're getting this unusual geometry. So why do we get this unusual geometry? Well, the explanation is a little bit complicated, but it kind of goes like this: is that the carbonyl is said to come in, turn 90 degrees, and essentially, in other words, the hydrogen approaches the phosphorus. That makes a little sense because sterically that's the smallest group. And as it comes in 90 degrees like that, okay, this is the intermediate. This is called the beta-ene because it's this multi-charged species. Now, if it comes in this way, but of course to form the double bond, it has to form the bond to the phosphorus, the oxygen has to turn. When it turns this way, you can see it forms this four-membered ring. Again, this is a lot like the intermediate in olefin metathesis, but it puts the two substituents cis to each other in this four-membered ring. So now when it falls apart, you get your Z configuration, your cis configuration of your alkene. So that seems to work. And so reliably, you can get a cis product, but of course the trans product would be the thermodynamic product. So it's definitely a kinetic phenomena that we're looking at. So the thermodynamic product, of course, is something that you might like to have, and we'll see in a second how to get that. Now, stereoselectivity is much better with aldehydes than ketones, because if instead of an H here you have some other alkyl group, of course the steric argument doesn't work very well. If it's a methyl, I suppose, and something really huge over here, it's still going to work for a ketone. But as soon as your two sides of a ketone get any size, then this whole stereoselectivity argument is kind of out the window, and you're going to get a mixture of geometries. So let's devise a Wittig synthesis. So here, look at these candidates here. Pause the video for a second, and select the one that you think is going to work. So, okay. What are we going to look for? Well, the best thing to do is to count the sides. So here we have the phenyl, there's one methylene, and then this needs to be the carbonyl. So we have to act for methylene in there. So these two lack those methylenes, so it has to be C or D. So then let's count from the other side, and we have 1, 2 carbons, and then this has to be a third carbon, which would of course be attached to the phosphorus in the ylide. So there has to be 3 carbons, And so we need look down here, here's the 3 carbon one is this one, and so the answer has to be C. Okay, now the nice thing about a Wittig synthesis, however, is that you can always approach it from two directions. We could turn this thing all around and we could look at it from the other direction. So let's do the same problem again. Again, the aldehyde, we have a 1, 1, 2, then the aldehyde. So 1, 2, then the aldehyde. So it's B or D. And over here, what we have is we have one methylene and then another carbon which has to attach the bromide. And so before we had B or D, and this goes just 1, 2 carbons, it's B. So I hope you figured that out. Okay, so this nice thing, you can always look at a Wittig coming from either direction. It just depends which set of starting materials can you put together easier. Okay, what about this business of getting the thermodynamic product? Well, thermodynamic product means you want to go to equilibrium. And it turns out that a extra mole of base will favor the E product. And what's thought to actually happen is that when you form that beta E, that intermediate species here where you have that square intermediate, is that there's an equilibration. So this is a figure I stole out of the Wikipedia, but here's you're showing your Wittig reagent. The aldehyde comes in. This is that beta E, this charged intermediate thing where the O- is trying to line up with the phosphorus to form the four-membered ring. At this point, they're showing throw in a mole of phenolithium, and you do a equilibration. And this equilibration is basically means that you simply deprotonate the hydrogen here, and this lithium is just a very polar bond. It's very easy to flip the configuration with the lithium on there. So it flips over to the trans isomer in that four-membered ring, which ultimately gives you the E alkene. That's the theory anyway. But basically you throw in an extra mole of a lithium compound, and you've got your compound. Now it says phenolithium here too. Is you could use another mole, butyllithium, in Oscar uses butyllithium. So 1 mole base phenolithium. Okay. So the ylids containing resonance stabilizing groups are not very reactive. So it turns out if you delocalize the negative charge here into some substituent, then the reactivity just goes down, and then they won't necessarily react with an aldehyde or a ketone. And that is, of course, a severe restriction on that. But, of course, the way to get around with that is to simply use a more reactive phosphine. And so so what people do is they leave phosphenes, and they go to these guys who actually are phosphites. And with that extra oxygen on there, it turns out it makes this whole thing much more reactive, because these are electron withdrawing, so that basically just increases the reactivity of the whole thing. So your alkylation is a little bit different now, because when you alkylate, it turns out that the whole things, you get this, you basically kick out an alcohol here, and you end up with this double bond O. So the intermediates are very different, but they work basically the same. This is called the HWE modification. Horner, Wadsworth, Emmons are the people who invented this, and so these are the ones that you use when there's conjugated groups on your carbon. So and it turns out that these things give you automatically the thermodynamic product. It's less reactive, and they explore the energy surface more, and they give you the thermodynamic product. So, but what if you want the Z isomer? What if you want the kinetic product? Well, what people do is they modify it once again, and they use this this very strange reagent here with trifluoral methyl groups out here on the end, and it turns out this one here is reactive enough to go back to a kinetic product, and allows you to make the Z isomer again, even with conjugated groups. Now this one we're not going to talk about too much, but it's here to make the story complete. And this is called the still HWE reaction. So there's actually, I give you 4 variants here now, which seems like maybe more than we need. But anyway, let's just summarize these. A normal unstabilized illid is a normal Wittig. This is the one we'll talk about the most, or you'll use the most. Gives you these Z configuration. For unstabilized illids, this is the throw in the extra mole of base. It says phenolithium here. Butyllithium works as well. That's the one that's in Oscar, and you get the E isomer. When you go to a stabilized illid, in other words, delocalization into here, this would be a phenyl group or a carbonyl or something over here. The HWE method gives you the E isomer, and then this still method where you use this other even weirder looking phosphine gives you the Z isomer against. The first 3 of these are programmed in Oscar C, and this last one is not, and that's because I'm lazy and I haven't done it yet. Okay, so let's work through and see an example, and you'll have some more examples. Well, actually, this example's in the problems below, but we'll have some more examples as well. So here we've got a aldehyde. I'm going to protect it, turn it into a lithium reagent, add a mole of formaldehyde and work it up. That's going to give me compound X. We're going to do a Wittig with that. We're going to then do an oxidation of something or other to get Y. That's going to do another Wittig, and make us compound Z. So what is compound Z? And this once you pause it right here and work the problem below, and come back, and then we'll look at the answers. Okay, pausing. You didn't pause. I know you didn't, but let's look at the answers anyway. Okay, so here are the possibilities. So how do we work this out? Well, let's do it one at a time. This is going to be compound X, right? So we protected the aldehyde with the ethylene glycol. We formed a lithium reagent from the bromide. We added a mole of formaldehyde, and then we worked it up in acid. The acid did 2 things. It neutralized the alkoxide here, and of course it released the protecting group. So this is compound X. Then with compound X, we reacted with a Wittig. We expect a Z isomer. Okay, so here is Y. And now at the other end, we're going to throw in a mole of phenolithium to get Z. So on the other end, we're going to add the same group, but it's going to be the E isomer. So which compound is that? If you look through here, we're going to have a methyl on each end, 1 Z and 1 E, and that is compound E. So I hope you figured that out, and it shows you how nicely this all stuff works. Now here's a classic example from the literature. This is more complicated than anything we'll ever do. So here's an aldehyde at one end and an acetal at the other, which of course is a protected aldehyde. That's something to keep in mind. And here's reaction. So they do a conventional Wittig, and of course they get a Z isomer, or they do the conventional Wittig with a mole of butyllithium thrown in. This is the so-called Schlosser modification, and this gives you the E modification. Now they have these 2 compounds, and one's you got from thermodynamic control, the other one from kinetic control. Now we're going to take the one that was from kinetic control, and we're going to free up some protons. We're going to free up the aldehyde at this end, and now we're going to add another Wittig, but this is a conjugated one. It's got a carbonyl there, and so this gives us the HWE gives us off the bat the E isomer, and then we could do the opposite. We could use the still method, and that gives us the Z isomer. So there we keep making this thing longer. We have 2 possibilities. So if you look at the whole plan here, is when you put these things all together, you can make, here we have a central double bond and then 2 double bonds on either side. And depending on what route we take through this chemistry, we can make all 4 isomers of the outer 2 double bonds. And that just shows you what a great reaction the Wittig reaction is. We call it the great synthetic reaction number 1. What's number 2, you ask? Well, it's going to be the Diels-Alder reaction, which we'll talk about in the coming lectures. So anyway, that's it for today, and welcome to the Wittig reaction.